Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
Good to be back.
Today we're doing a deep dive into, well, really the language that defines manufacturing quality. Geometric dimensioning and tolerancing GD&T. And specifically, we're hitting the absolute bedrock of interchangeable design. Limits and fits for holes and shafts.
Yeah, this is fundamental stuff. We are simplifying a huge stack of documentation today.
Sounds ambitious.
Well, our mission is to take the latest ASME Y14.5 2018 changes, sort of pair them up with the global ISO 286 fit system, and give you clear guidance on selecting the exact tolerance code you need.
Right, so parts actually fit together.
Exactly, to ensure your parts mate perfectly, cost-effectively every single time without, just guessing.
We've synthesized material covering these latest standard revisions, the international ISO fit codes, and importantly, the harsh practical realities of tolerance analysis and metrology.
Because your drawing, it really is a contract, isn't it?
It absolutely is.
And if that language isn't precise, the contract fails. That opens the door to, well, massive scrap and rework costs.
Definitely want to avoid that. So let's start with the language itself, GD&T. How has it been evolving?
Well, GD&T is essentially that concise, universally understood, symbol-based language. It defines geometry and, crucially, it controls part variation.
Making clear design definition possible.
Exactly. It makes it possible.
And you mentioned the ASME Y14.5 standard from 2018. It seems like it cleaned up quite a bit of legacy ambiguity.
It really did.
What are the biggest updates engineers really need to know right now?
I'd say the most foundational shift is probably the dimension target rule, Rule 4.1Q.
Okay.
It clarifies that the nominal dimension value, let's say 32.0 on the drawing, that value is not the manufacturing target.
Wait, hang on. If I put, say, 32.0 plus or minus 0.02 on a drawing, the target isn't 32.0.
Nope.
But isn't that what we've always intuitively assumed the supplier should aim for?
That assumption is precisely what's gone now. The standard says the target must be the middle of the tolerance zone.
So if your tolerance zone is asymmetric, like 32.0 plus 0.02 minus 0.00.
Right, a common scenario.
Then the supplier's production goal, their target, must be 32.01.
Yeah.
Right in the middle.
Okay, that eliminates potential arguments about, where they should center their production runs.
Exactly. No more ambiguity there.
That's a pretty fundamental change in thinking.
It is.
And speaking of cleanup, what about those confusing legacy symbols? Engineers have kind of avoided them for years, haven't they? Did Y14.5 finally get rid of concentricity and symmetry?
They did, thankfully. The standard has officially eliminated concentricity, that's the circle symbol, and symmetry, the three horizontal line symbol.
The term, the symbol, everything.
Term, symbol, and the whole concept. Gone. Mostly due to decades of confusion and, frankly, misapplication.
So what's the recommended practice now for controlling coaxial features?
If you need to control the location of coaxial features, the modern and frankly superior alternatives are position and runout. They do the job much more clearly. Okay, that simplifies things a lot by just removing tools that were often misused or misunderstood.
Definitely.
What about defining the actual object itself? Any changes there?
Yeah, they clarified the definition of a surface too. That's 4.1S. It says elements of a surface must now explicitly include surface texture and flaws.
Flaws like burrs and scratches.
Exactly. Burrs, scratches, waviness, all those elements have to stay within the tolerance zone boundaries, unless you specifically state otherwise.
Okay, so that's the ASME world trying to be clearer. But manufacturing, it's global, right? And that means we run smack into the fundamental challenge. The philosophical differences between ASME Y14.5 and the ISO standards, like ISO 1101 and 286.
Right. And this is a big one. They agree maybe, 65 to 95% of the time, depending on the specific aspect.
Yeah, something like that.
But the biggest risk, the place you can really get tripped up, lies in how size is defined and controlled.
How so?
Well, ASME generally treats a size tolerance as controlling both the local size and the actual mating size, or the envelope.
Which seems intuitive, right? If my hole measures within its plus-minus tolerance, I assume it's round enough and straight enough to mate properly.
And that is exactly the trap when you step into the ISO world. Under ISO 1101, the basic size tolerance only controls a 2-point size measurement, like caliper jaws. Yeah. If you rely on that ASME intuition, you completely lose control over the form, the roundness, the straightness, unless you explicitly add the envelope symbol, that's the circle with an E inside, to control that essential mating size.
Wow. So just relying on old habits when switching standards could mean a part is technically in STEC based on a 2-point check, but it's functionally useless because it won't assemble.
Precisely. That's a huge hidden risk, especially for multinational companies working across different regions or with different suppliers.
That is a critical distinction.
And just to sort of close out this ambiguity section,
Right.
the 2018 standard also cleared up that old headache around radius or R tolerance.
Ah, yes, the R versus diameter confusion.
Right. The clarification is, if the center of the radius is located using dimensions, then the resulting arcs must be concentric.
Okay.
This gets rid of that old ambiguity where radius didn't necessarily equal half the diameter in terms of form control. The good practice is still only use plus-minus tolerances on features you can easily check with calipers, like widths or simple diameters. Use GD&T for anything more complex.
That focus on clear measurement, especially for features that aren't just simple widths, brings us right back to mating parts. If we can't just use a caliper for everything, we need that more sophisticated language of fits, which is primarily defined by ISO 286. This is how we ensure parts actually interact the way we design them to.
Exactly. The fit describes that required relationship between the mating parts, typically a hole and a shaft. ISO 286 sets up the whole code system for tolerances on these linear sizes.
And these fits fall into basically 3 categories, right? Based on how their tolerance zones interact.
That's right. It's all about whether you guarantee clearance, guarantee interference, or allow for either possibility.
Okay, let's start with the 2 extremes. What's the first one?
So the first is the clearance fit. This one always provides a gap, a clearance, between the hole and the shaft after assembly. Meaning the smallest possible hole, its lower limit, or LLS, is still greater than or equal to the largest possible shaft, its upper limit, or ULS.
And you'd use this when?
You use this when parts absolutely need to slide or rotate easily. Think loose bushings, sliding guides. No tools should be needed to assemble them.
Okay, easy movement. What about the opposite end, the really tight high-stress joint?
That would be the interference fit. This one always provides an interference, basically a negative difference in size before assembly.
So the shaft is always bigger than the hole, essentially.
Correct. The upper limit of the hole size is smaller than or equal to the lower limit of the shaft size.
And this requires...
This always requires force or thermal methods for assembly. Think press fits for bearings or dowel pins, shrink fits for gear hubs. It creates a permanent high torque or high load carrying joint.
Right. So clearance for movement, interference for fixed joints. What about the middle ground, where it's not quite guaranteed either way?
That's the transition fit. Here, the tolerance intervals, the zones for the hole and the shaft actually overlap.
Meaning the final assembly.
It may result in a small clearance, or it may result in a small interference. It depends on where the actual manufactured sizes fall within their allowed ranges.
So why use that? Seems uncertain.
It's ideal for parts that need a really secure, reliable location and connection, but perhaps might need to be disassembled later without, destroying everything. Accurate location fits, like for inner bearing rings under moderate loads.
Okay, makes sense. Now, when designers are applying these fits, they often hear about the hole basis system, usually denoted with a capital H, versus the shaft basis system with a lowercase h.
Yes.
If I'm setting up, say, a new production line or just standardizing practices, which one should I generally lean towards, and why does that choice really impact manufacturing cost?
Great question. You almost universally choose the hole basis system, symbolized by that capital H for the hole's fundamental deviation.
Why the hole?
The reason is purely manufacturing practicality and cost. Think about how holes are typically made, drills, reamers. These are often fixed, standardized, sometimes expensive tools.
Right.
By fixing the hole size, specifically setting its lower limit deviation EI to 0, which is what the H signifies.
You mean the smallest allowed hole is exactly the nominal size?
Precisely. By doing that, you minimize the need for lots of different specialized hole-making tools. You achieve the desired fit clearance, transition, interference by varying the tolerance on the shaft, which is usually easier and cheaper to machine to a specific size.
Got it. So you standardize the expensive, often less flexible manufacturing step making the hole, and manage the actual fit by adjusting the component that's typically easier and cheaper to customize, which is the shaft.
You've got it. The shaft basis system, using the small h where the shaft's upper limit deviation is 0, is much less common.
When might you use it?
It's typically reserved for more specialized applications. Maybe you're using expensive, pre-finished, precision ground shafting as your raw material, and you don't want to machine it further.
Okay.
Or perhaps you have a single long shaft where you need to mount several different components, each requiring a different type of fit along its length. Then it might make sense to keep the shaft consistent and vary the holes, but generally, whole basis is the way to go.
Let's make this really concrete then for the listener. Give us, say, the 3 most essential ISO-fit codes using that preferred whole basis system that every mechanical designer should probably have in their mental toolbox.
Okay, 3 key examples using whole basis H holes. Remember, holes are capital letters, shafts are lowercase.
Got it.
First, for a normal running fit, you need parts to move relatively freely, maybe like sleeve bearings running at decent speeds. You'd specify H7, F7. That F shaft designation guarantees a defined clearance with the H7 hole.
H7, F7. Go running fit. What about a press fit, like for gear?
Right, if you need a gear wheel or maybe a bearing bush pressed into a housing, something that has to withstand high torque and basically be permanent, that requires an interference fit. A common choice would be a medium press fit, like H7P6. H7P6. That P-shaft is designed to be consistently slightly oversized relative to the H7 hole tolerance zone. You'll need significant force.
Okay, and the middle one, the
Yeah.
transition fit, like for locating something accurately but maybe needing to remove it later.
Exactly. For that kind of transition fit secure, reliable location, but potentially removable, like positioning the inner ring of a standard ball bearing under average loading conditions, a good choice is the push fit, often specified as H7K6.
H10K6.
Here, that K-shaft tolerance zone actually overlaps the H7 hole zone, so you might get slight interference, might get slight clearance, but it provides very good centering and location without extreme force.
H77 for running, H7P6 for press fit, H7K6 for transition location. That clarity is exactly what designers need.
Those 3 cover a huge range of common applications.
But, even with perfect GD&T on the drawing and the right ISO fit specified, measurement itself can still throw a wrench in the works.
Oh, absolutely.
Let's talk about the inspector's dilemma, especially this issue of measurement divergence.
Yeah, this is where theory meets reality, often painfully. Even when the drawing is crystal clear, how the part is actually measured is surprisingly complex.
How so?
Different CMMs, coordinate measuring machines, use different software algorithms to interpret the cloud of points they collect off a surface, and different yet equally valid algorithms like, say, least squares, minimum zone, or maximum inscribed can measure the very same feature on the very same part and return significantly different results for things like size or position.
And this isn't just theoretical, right? This has caused real problems. I seem to recall reading about a GI-Devel alert, like an industry warning, back in 1988.
That's right, GIDEP or F3A A8801.
And it basically shut down CMM use for verifying GD&T in some high-reliability industries for a while because engineers just couldn't trust the numbers coming off different machines or different software.
Exactly. The results weren't repeatable or correlatable enough between systems, leading to good parts being rejected and bad parts potentially being accepted.
Why does the most common algorithm, least squares, cause so much controversy? It sounds reasonable.
Well, least squares is mathematically straightforward, easy to implement in software, and it gives very repeatable results on the same machine. That's its appeal.
Right.
But it works by averaging all the data points to find the best fit geometry. If there's an anomaly on the surface, like a piece of dirt, a small burr, maybe some waviness, it averages that error into the definition of the feature.
So it might smooth out a critical local deviation that could actually affect function.
Precisely. It might make a slightly out-of-spec feature look acceptable on paper because the average fits.
Yeah.
This is why some quality professionals kind of cynically joke that relying solely on least squares means sometimes the statistically averaged wrong is best, simply because it gives you the same wrong number every time. It doesn't always reflect true functional reality.
That adds a whole layer of fundamental uncertainty to every measurement, doesn't it?
It really does. Measurement is not as absolute as we sometimes like to think.
Okay, now if we multiply the single part measurement uncertainty across an entire assembly of multiple parts, we run headfirst into the massive headache of tolerance stacking or tolerance analysis.
Yeah, managing the dimensional chains in an assembly is critical. You basically have 2 core methods for predicting the final assembly variation.
What's the first way?
The first is arithmetic tolerancing, sometimes called worst-case tolerancing. This is the most conservative approach.
How's it work?
It assumes the absolute extreme of every single tolerance in the chain combined simultaneously in the worst possible way to maximize the final assembly variation. Smallest possible dimension here, largest possible there.
That sounds incredibly safe, guaranteeing 100% assembly success, but probably results in cripplingly tight and expensive tolerances on individual parts if the chain has more than a few components.
It absolutely does. The required assembly tolerance grows linearly with the number of parts. It guarantees certainty, but often at an unfeasible manufacturing cost.
So what's the more practical alternative?
The far more common, pragmatic, and cost-effective approach is statistical tolerancing, often using the root sum of squares, or RSS method.
Right, where you're basically making a statistical bet, aren't you?
You are. You assume that the variations on individual parts are independent and random, often following something like a normal distribution centered in their tolerance zones.
And the bet is that the deviations will usually tend to cancel each other out. Some parts slightly big, some slightly small.
Exactly. It's statistically very unlikely that all parts in an assembly will be at their absolute worst-case tolerance limit simultaneously.
And the benefit is?
The huge benefit is that the predicted assembly variation grows much more slowly, only proportional to the square root of the number of parts. Statistical tolerancing allows designers to assign wider, cheaper manufacturing tolerances to the individual components while still achieving a very high predictable level of certainty, say 99.73% for a ±3 sigma process in the final assembly outcome.
Okay, so the practical advice for designers seems pretty clear then. Don't just slap tight tolerances everywhere.
Please don't. Use the general tolerances in your title block, like ISO 2768 medium or fine, or equivalent ASME general notes for features that aren't critical to function or assembly. Let those float within reasonable shop practice. And only call out specific GD&T controls, like true position, maybe line profile or surface profile for complex shapes, for those features that are absolutely critical to function, interchangeability, or the key assembly interfaces.
Because if you over-tolerance everything.
If you put tight GD&T on non-critical features, you are forcing specialized manufacturing processes, complex inspection setups, maybe mandatory CMM checks unnecessarily. You're just multiplying your cost, often significantly, without adding any real functional value to the product.
Makes perfect sense. Use precision where it matters, not everywhere.
That's the essence of cost-effective design.
So, wrapping up, we've covered quite a bit. The evolution in GD&T standards like ASME Y14.5, getting rid of ambiguity, the fundamental principles of the ISO fit system, and how picking the right notation like H7F7 or H7P6 is really the key to predictable, cost-effective interchangeability.
We have. Understanding that language is crucial.
But if there's one single number, one statistic that really justifies mastering all this complexity, especially the GD&T side, it seems to come back to the power of true position tolerancing.
Yes, the bonus tolerance. That is probably the greatest hidden efficiency bonus unlocked by GD&T.
Explain that again. How does true position give you bonus tolerance?
Okay, think about locating a hole using traditional coordinate tolerancing, like x plus minus 0.1 and y plus minus 0.1. That defines a square tolerance zone for the center of the hole, 0.2 by 0.2.
Right, a square.
But true position, using the position symbol, defines a cylindrical or circular tolerance zone around the theoretically exact location.
Okay, a circle instead of a square.
So that circular zone has a diameter equal to the diagonal of the old square zone. It fully utilizes the corners that were previously unusable with coordinate tolerancing.
Which means the total permissible area where the hole's axis can actually fall is bigger.
Much bigger. That shift from a square zone to an equivalent circular zone, which GD&T enables, results in up to a 57% increase in the usable tolerance area for that hole's location compared to the coordinate method with the same deviation limits along the axis.
57%. That's huge.
It's massive. This hidden volume, this extra geometric space you gain, translates directly into greater manufacturing flexibility, fewer parts being scrapped for positional errors, and ultimately significant cost savings, especially in high-volume production.
That increase in usable tolerance area is genuinely shocking, especially when engineers are often fighting for just a few extra microns or tenths of a thou in other dimensions. It really proves that mastering these standards isn't just academic, it's essential for maximizing efficiency.
Absolutely. It's money left on the table if you're not using it correctly.
So for you, our listener, the immediate call to action seems crystal clear after this discussion.
It really is. Confirm today if you don't already know for sure whether your organization, your department, your key suppliers operate primarily under the ASME Y14.5 standard or the ISO 2861101 system.
Because knowing that difference.
Understanding that fundamental difference, especially regarding how size is controlled and whether you need that envelope symbol with ISO, is probably the single most critical first step. It impacts your design choices, your tolerance analysis, and how you interpret inspection reports. Get that wrong, and you're building risk right into your design process.